Good morning and good afternoon, everyone. Thank you for joining us. So this is the third WREN webinar titled Understanding Avian Collision Rate Modeling and discussing what this means in a population context at land-based and offshore wind farms. As Colin mentioned, my name is Luke Hanna. I'm with Pacific Northwest National Laboratory. Elise George from the National Renewable Energy Laboratory and I will be moderating this webinar. Elise will be providing a brief introduction for our speakers in a minute, but first, I'd just like to reiterate a couple of housekeeping items. As Colin mentioned, we will be taking verbal questions after the presentation, and he will provide instructions for that. We will, if for some reason there are technical difficulties or we are getting a lot of feedback, you may also click the send note button and send written questions to all moderators. And then finally, as Elise will mention, this webinar is being recorded and will be provided on the WREN Hub, and so she will have a URL to follow. So with that, I'd like to turn it over to Elise.
Thank you, Luke. This is Elise DeGeorge from the National Renewable Energy Laboratory. I wanted to share with you some information on what WREN is and a little bit of background on the WREN webinar series, and then we'll quickly launch into Mark and Angus's presentation. WREN stands for Working Together to Resolve the Environmental Effects of Wind Energy, and that is another name for the IEA Wind Task 34. It was originally approved by the IEA Wind Executive Committee in October 2012. Since that time, in September 2014, as you can see on the slide, we launched a webinar series. As Luke mentioned, we're now on the third of a quarterly webinar series, and this series has developed in support of WREN's goals to facilitate international collaboration that advances the global understanding of the environmental effects of onshore and land-based wind energy development, and to create a shared global knowledge base and community of practice around research, monitoring, and management of the environmental effects of wind energy development. We've had 2 webinars to date. Webinar number 1 was in September 2014, where Chris Hein of Bats Conservation International and Oliver Baer of the University of Erlangen in Germany covered the best practices for assessing the impacts of wind energy development on bats. The next quarter, in December 2014, we had Dr. Debbie Russell from University of St. Andrews and Ross McGregor from UK's Natural Power, covering the research efforts to measure seabird and marine mammal attraction and avoidance at offshore wind farms. The information from these past webinars and all future webinars can be found on the WREN Hub, and you will see the URL on a subsequent slide here. So today's webinar is on understanding avian collision risk rate modeling and discussing what this means in a population context. We're excited to have Mark Collier from WREN in the Netherlands and Angus Cook from the British Trust for Ornithology in the UK. If you need contact connection information, you can go right to this URL off the TEFIS database from PNNL, and this URL takes you right into the WREN Hub and gives you call-in information. And this is also the location for all future WREN webinar series information, amongst other things. So our speaker bios, Mark Collier and Angus Cook, their bios are provided on your screen. I'm just going to read off a small part of these bios, and they'll be sharing with you their experience and expertise throughout their presentations. Briefly, Mark Collier currently works as a bird ecologist at Bureau Waardenburg, a leading ecological consultancy in the Netherlands. He's originally from Britain. Mark studied applied ecology and conservation at the University of East Anglia in the UK and worked for both the Royal Society for the Protection of Birds and the British Trust for Ornithology before moving to the Netherlands in 2008. Since being at Bureau Waardenburg, Mark has been involved with various ornithological projects, including radar studies, satellite tracking, and wind farm studies, both on land and at sea. And you'll hear about his particular interests and expertise throughout his presentation. Briefly on Angus Cook, Angus has worked for the British Trust for Ornithology since completing his PhD at Newcastle University in November 2008. The interactions between birds and renewable energy have been a key focus of his work at the BTO, and one of the first projects he worked on was investigating the impacts of a tidal barrage proposed for the Severn estuary on waterbirds. Again, you'll hear more about Angus's expertise and interests throughout his presentation. So without further ado, Angus, I'll turn this over to you to start us off.
Thanks for the introduction, Elise. So throughout this talk, Mark and I are going to give a brief introduction into our respective organisations before Mark's going to give a sort of quick overview of birds and wind energy and how they go about monitoring collisions. Following that, I'll be giving a sort of quick introduction of the different models that are used to estimate collision rates before focusing on the BAN model, which is one of the most widely used at present. And I'll be discussing the sort of sensitivities and the knowledge gaps associated with those models before Mark's then going to try and explain how the results are put into a population context, and then finally I'll try and describe how the outputs from these models are used by decision makers. So the British Trust for Ornithology is an independent and impartial research organisation, and the impartial part of that is particularly important. We're perfectly happy to give guidance on what we feel the evidence suggests that the impact of any development will be, but we won't then go on to say whether or not we think that development should take place. And because of this, we're well placed to provide advice to a range of regulators and governmental advisors, but we also do work for industry. Some of our key projects recently with the offshore wind industry have included running the strategic ornithological support services, which aim to provide support to both industry and regulators in the planning of offshore wind farms. We've been involved in the environmental impact assessment for the Dogger Bank zone. Two of the wind farms in the zone, Creekbeck A and Creekbeck B, have recently been granted planning consent and will become two of the biggest offshore wind farms in the world. We've been involved in seabird tagging to look at the movements of birds in and around offshore wind farm, and we've also conducted several key reviews of survey methodology, understanding how the data are collected within an offshore wind farm, modelling seabird flight height and avoidance behaviour, collision risk modelling methodologies, and also understanding how post-consent monitoring is carried out. But our aim in all of this is to ensure that all decisions that are made are based on the best available evidence. I'll just pass you over to Mark, who's going to give you a bit of an introduction to me.
Hello, this is Mark Collier, and as we mentioned, I work for Bureau Waardenburg, which is a research consultancy in the Netherlands. There's around 75 staff here carrying out research in all areas of ecology, and I work myself for the bird ecology department along with 14 other people. We carry out a number of projects, mainly in the Netherlands, but also in other countries. And rather like the BTO, we have an independent and objective approach. So we advise based on the evidence. So we carry out a lot of practical projects, collecting data to then inform and advise. Now, wind energy has been a topic here since the early 1990s, and the very first studies were undertaken using small mobile radars, and in that time we've moved on to using automated radar systems, including at the first Dutch offshore wind farm, as well as at other locations in the North Sea to try and calibrate and gather more information on bird movements with regards to collisions at wind farms. And it's rather nice that the BTO and Bureau Waardenburg are doing this presentation together. You'll see here a map of the North Sea with the planned areas for offshore wind farms. The dotted lines give the national boundaries, but of course we all know that the birds don't recognize those. So it's very fitting that we do often work together and share information. And for example, Angus has already mentioned the SOS group, where we were also involved in writing several of the reports and as a partner. BTO are carrying out at the moment tracking studies using GPS loggers on gulls in relation to wind farms. And in the Netherlands, we're also carrying out similar work. And recently, we carried out, or we organized a joint symposium regarding birds and wind turbines. So just to introduce the issue of birds and wind energy, there are several effects that can be defined in a number of ways. The first one is really sort of the displacement of birds to other areas. And this can be as a result of several processes. The very first one is habitat loss. And in wind turbines, this is actually quite limited. The footprint of turbines is actually quite small. Quite often, infrastructure is already nearby. So this is quite restricted to specific locations, perhaps specific habitats or specific species. The second process is disturbance. And this again seems to be, for most species, quite limited. So in a study in the Netherlands, Buick swans at the start of the season showed a preference for foraging further away from the turbines, but as food was depleted, they moved closer and closer to the turbines, and there was actually, across the whole season, very little displacement from the areas close to the turbines. However, this will become more important with increasing numbers of wind farms, and again, perhaps for sensitive species or certain habitats. Displacement can also occur through barrier effects, so birds might be prevented from reaching certain areas or certain habitats physically by the presence of the wind turbines. So they either have to fly further to go around them to reach those habitats, or they might decide that that's not energetically feasible, so they will be prevented from reaching those areas. Again, this is mainly limited to certain areas, perhaps if you consider breeding birds where they're very attached to certain areas for certain times of the year, and they want to go to foraging areas. A study looking at Barre effects in relation to migration found that this had actually very little effects, and the extra distance travelled to go around wind farms is actually quite small. However, as with other effects, with increasing numbers of wind farms, then the effects of these are likely to be combined together. Now, the result of birds not being able to reach certain habitats is that survival might be affected indirectly. They might not be able to forage optimally, and survival might be lower, or breeding success, for example. However, collisions have a direct effect on mortality. So once a bird's been hit, then we assume it's died, it's been removed from the population. So because of this, until now, this has really attracted the most attention, and most research is looking at collisions on birds. Now, current estimates are from less than 1 collision to around 30 collisions per turbine per year, and some studies really have this much higher figures, perhaps up to 60 or more collisions per turbine per year. There are very few figures for offshore, and we'll come back to this, but it's expected that the numbers of collisions are likely to be lower, and this is largely due to lower flight intensities offshore. Now, in the box is a very well-known example of a certain wind farm where there quite high numbers of collisions have been recorded. And the variation we see in the estimates of numbers of collisions per turbine are really due to the numbers of birds in the area. And this varies hugely per location, but also time of year or time of day even, and also the species and what their species are doing at that moment. So of course, to record the number of collisions, well, that's quite straightforward. We can actually go out and do either daily or weekly searches. We do need to make corrections for searcher efficiency, so perhaps in long grass we're going to find less than on flat roads or easy to search areas, and also the type of species, so a large white swan will be very visible compared to a small brown songbird. And some studies actually also use dogs to increase the chance of finding victims. And this type of monitoring is very useful to fill obligations for wind farms, as well as building on knowledge of bird and wind turbine interactions. And we can actually use these types of data on numbers of collisions with studies on flight intensity to try and come up with some sort of collision risk. However, the disadvantages are it's quite labor intensive, especially for larger wind farms. If you're imagining hundreds of turbines, that would take quite a long time to search. There's not always access to wind farm locations, and I've already hinted on, some habitats are quite difficult to search through, and particularly offshore this becomes an issue, that we can't search offshore. Birds that collide with turbines very quickly sink or float away, and we're not able to find them. And also pre-construction. So before a wind farm is built, then obviously we also can't count the number of collisions. So as mentioned, offshore it's very difficult to find victims. That's not possible due to the habitat. Perhaps we could count the collisions. So unfortunately, it's just too few. So based on the figures on the last slide, there'd be a collision with a turbine every 2 weeks to 20 years. And quite often these will occur at night or in poor weather where it's not possible to access offshore areas. So ideally we want an automatic registration system. Sounds very nice. So a bird flies along, hits the turbine, and a photograph or even better video footage is recorded and then sent to us automatically to our computer at our desk. So that sounds very nice. Now there's a couple of systems which are in advanced stages of development and actually being used. One of these is being tested now with cameras, or will shortly be tested with cameras at an offshore wind farm, and another system is being used at present. However, most of these systems still need development and validation. There's a review available through the SOS website, and there's no really plug-and-play system at the moment, so there's a lot of development and validation needed, and of course pre-construction, these also aren't possible. So that's really why we need collision rate modeling, and as is shown here. Now the number of birds we can actually use, here's a radar image showing the number of birds. So this is actually something we can record in the field, so the number of birds flying through an area. However, to get to the number of collisions, we also need an idea of collision risk. And some areas of this, we can also use field data to inform the collision risk. So that would be things like avoidance, or perhaps the probability of a bird flying through a rotor. However, certain aspects of this, we do need modeling because they're difficult to measure in the field. So modeling, it's not a complete method by itself, we do need field data to inform modeling, but it's very important at present. So modeling can be important prior to construction to inform perhaps planning the type of turbines that would be best or the numbers of turbines. It's also possible for informing at inaccessible locations where collision victim searches aren't possible, and certainly for vulnerable species that perhaps might need special attention. And there's a range of models, and just to list a couple here, that have been commonly used in the past. There's some empirical models that are based on field data and then make a correction on different types of turbines and numbers of turbines. And there's more theoretical-based models, such as the band model, which Angus will talk about in more detail.
Yeah, thanks, Mark. So, as Mark's just outlined, one of the key reasons we need to do collision risk modelling is to understand what the likely risk to birds is before a wind farm is built. There are a variety of collision risk models, but at the heart, most of them contain some information about the bird data and some information about the turbine, although crucially they don't generally include any estimates of uncertainty or variation surrounding those parameters. At their core, they usually calculate the probability of a bird colliding from a single transit of the rotor swept area of a turbine, and this is usually based on the probability of a turbine blade occupying the same space as the bird at the same time as the bird is passing through the rotor. This value is then generally scaled up using survey data and applied across the total numbers of birds passing through the wind farm, and then adding in an element of behaviour which is usually referred to as the avoidance rate, and then the output is usually given as a single number of collisions. And then again, there are issues with this which I'll come on to in a second. So there are a variety of models available. The point of this slide is just to illustrate that there are a variety of different models, and they all do similar but different things. So some of them take account of the fact that you've got the turbine tower as well. Some of them ignore that. Some of them account for differences in speed and direction of the birds. Some of them account for the fact that the birds approach the turbine blades at different angles. And then the outputs can differ as well between the total number of birds colliding, the probability of birds colliding, and overall mortality rate. So that's just to illustrate the sort of range of different models available and how they do subtly different things. But as Mark's already mentioned, one of the most widely used, certainly in the UK, is the BAN model. It was originally developed by Scottish Natural Heritage for use with the Onshore wind farm, and it's subsequently been adapted for use in the offshore environment. Many of you may be familiar with the sort of various iterations of the spreadsheets that have been used that have been developed for use with this model. The top one here is the sort of basic model that was developed for onshore use, and then the lower images of the more advanced BAN model, which was developed as part of the SOS program for use in the offshore environment. There were a number of key changes between the onshore and the offshore models. The first was that rather than using count data for the number of birds passing through the wind farm, the offshore model uses a density estimate of the number of birds within the wind farm, which better reflects the way that data are collected in the offshore environment. It also allows monthly estimates of the number of birds present, so you can see the impact of things like migration or breeding seasons on the total collision estimate. And possibly most usefully, there's a number of different options for incorporating the proportion of birds believed to be at rotor height. So there's three options for this new offshore model. The first option is that you base the estimate of birds at rotor height on the survey data which you collect from the site concerns. Alternatively, you can use a distribution from a generic model to estimate the proportion of birds at risk height. And finally, the extended model allows you to take into account the fact that the collision risk varies with the height of the rotor, and I'll come on to that in a bit more detail later. So I'm going to sort of highlight three key sensitivities that this model has to the input parameter. The first of these has been really well publicised, and I think most people are aware of. It's the avoidance rate, the proportion of birds which, when approaching the turbine, will take some sort of action to avoid colliding. The second one, which I just touched on a second ago, is flight height, the sort of proportion of birds at rotor height, and therefore that are at risk of colliding. And then finally, flight speed, which is something that not a lot of people have looked at, but which is actually quite important, and I'll come on to that in a bit more detail later. So, based on work that Dan Chamberlain did validating the SNH collision risk model, the avoidance rate was highlighted as the key parameter in the model. A 10% change in the avoidance rate resulted in over a 2,000% increase in the predicted collision rate. This wasn't quite right, and I'll come on to that in a bit more detail later, but avoidance is still a very important parameter for collision risk models. And despite everyone acknowledging the importance of this parameter, the evidence base with which to draw conclusions from is extremely weak. So to address these different difficulties, Marine Scotland Science commissioned BTO and UHI to undertake a major review of avoidance rate in relation to offshore wind farms. So our sort of review highlighted that you can estimate the avoidance rate in two different ways, either through direct measurement, through things like radar or visual observations, or you can compare the recorded number of collisions to the number of birds that are passing through the wind farm, and use the number of birds to pass through the wind farm to estimate how many collisions you would expect if none of them are avoiding. So we find that the first challenge in coming up with a sensible avoidance rate for offshore wind farms was defining the spatial scales at which avoidance behaviour takes place. There's strong evidence that there's that birds are displaced from within offshore wind farms, and this is going to reduce the number of birds available to collide, so you need to take that into account when you're doing your modelling. But then within the wind farm itself, there's birds that will either generally try and avoid the area of the turbines, or birds that will just take an absolute last second action to avoid collision. We need to capture all three of these aspects when we're coming up with an overall avoidance rate, and we've sort of referred to them as macro for this broad scale, the meso for this within wind farm finer scale, and then micro is the absolute last second avoidance action. And these all three of these have been measured by different people and in different ways, but drawing them together we found to be particularly challenging. So we found that some of the strongest evidence we found was for macro avoidance, and we found a relatively large number of studies to draw evidence from, looking at aspects of behaviour such as barrier effects, where birds fly around the wind farm rather than through it, and displacement or habitat loss, where birds just generally avoid entering the wind farm to forage. We found that these rates were likely to be highly species specific, so several studies found that gannets had a very strong macro response rate to the wind farm, so following construction of the wind farm, the number of birds foraging within the area reduced by anything from 60 to 80%. In contrast with this, we found that the situation with gulls was much less clear, with some studies suggesting that a fairly weak avoidance response, and others suggesting that they might even be attracted to the wind farm potentially as a result of increased foraging opportunities. We found that when we looked at the meso and microscale, we found that there was much less evidence available. One of the key studies we did find was the Egmond-Dunzee data, which combined radar and visual observations in the Netherlands. But aside from that, to get a really good understanding of what was going on, we found that we needed to draw from evidence from onshore sites where collision rates were combined with an estimated flux rate, and we identified 20 sites in the UK, Europe and US where these data were available, and most of these data were focused on gulls, although there were some studies from terns, notably at the Belgian coastal sites. And if we know the number of birds colliding with the wind farm, and we know the number of birds passing through the wind farm, then we can calculate the avoidance rates by dividing the number of collisions we observe by the flux rate multiplied by the probability of any bird colliding. And this sort of really helped. We found that doing this really helped us to get a clearer understanding of what sort of avoidance rates might be realistic. So when we looked at this, we found that this sort of combined meso-micro avoidance rate was certainly above 99% for gulls, and possibly in the region of 99.5%. But given that we felt that there was no clear evidence of macro avoidance for gulls, we felt that suggesting a rate of 99% would be most realistic. Unfortunately, at this sort of meso-micro scale, we felt we weren't able to identify any evidence for gannet. However, given the high macro avoidance that gannets show, and the fact that that the avoidance rates for gulls were so high, we didn't think that avoidance behaviour in gannets was likely to be any lower than it was in gulls. So the second aspect that the collision risk models are sensitive to is the flight height and the proportion of birds at risk height. Recent analysis by Liz Masden of UHI has shown that actually the percentage of birds at risk height is equally as important in terms of the number of collisions predicted as the avoidance rate. The reason for this is that in the original Chamberlain study, they looked at the avoidance rate, whereas the parameter that goes into the collision risk model is actually 1 minus the avoidance rate. And if you look at this, then it turns out that the percentage of birds at risk height comes out as being equally as important. Typically, the proportion of birds at risk height is estimated by observers in boat surveys, but who assign them to a sort of series of flight height bands, usually designated based on objects like the height of the lower range of the rotor sweep or the height of the survey vessel mast. But there are several problems with this. First off, by taking estimates from boat surveys, they reflect height above mean sea level, whereas the turbines have to be 22 metres above the highest astronomic tide. And on some sites where these wind farms are proposed, this can actually be quite a significant difference. These heights are quite restrictive, as they don't allow you to consider what the impact of raising or lowering a turbine height might be. That's quite a key mitigation measure that some developers in the UK are considering. So they want to determine whether or not they can reduce the risk of collision and thereby the risk to birds, and get an easier path through the consenting process if they use a slightly larger turbine or a slightly smaller turbine. And also, they don't offer any sort of understanding of the uncertainty surrounding the flight heights. They just assume that a fixed percentage of birds will fly at this height, which isn't a particularly realistic assumption. There's also a number of analytical issues with this. Firstly, it assumes that all the birds will be distributed evenly within the rotor swept area. We know this isn't realistic. We know that birds are more likely to fly at lower altitudes than higher altitudes, and we need to sort of take this into account, given that a rotor area is circular rather than a cube. So you need to account for the fact that towards the lower reach of the more birds will be clustered towards the lower reach of the turbine rotor, where a lower proportion of it will be covered by the turbine rotor sweep. We also know that collision risk isn't constant within a rotor sweep. The way the sort of basic simple band model works, it assumes that the collision risk is treated as being constant within an average over the rotor swept area, but in actual fact it's variable. And if you look at this lower graph here, you can see that that actually the probability of collision is potentially significantly overestimated by assuming that the risk is constant within the rotor sweep. So to get around this as part of the SOS work, we combine the boat data using statistical models to produce a series of continuous distributions, like the one I've shown here on this slide, which is for sandwich turn, and this sort of shows a very, very clear drop-off around sort of 10 to 15 meters in the number of birds at any given height. By combining data across from multiple surveys, we can also get an estimate of the uncertainty surrounding this, and that's useful for the collision risk modelling process. And these are incorporated in what's referred to as the extended band model, or option 3 of the band model. At present, we're also working with people collecting digital aerial survey data to produce similar distributions from their data. Flight speed's another parameter which the collision risk models are sensitive to, and it's one that's been largely ignored, which is strange given that actually it goes into the collision risk model, or the BAN model, twice. First of all, it's used to estimate the flux rate of the number of birds passing through the wind farm. So the density of birds is known, and it's assumed that each of them will be travelling at a given speed, and you can extrapolate that out to work out the total number of birds that are likely to pass through the wind farm at any given time, or over any given time period. And it's also used to calculate the probability of collisions, so the probability of a bird flying through a rotor sweep and passing through the rotor sweep at the same time as a bird is passing through its flight path. There's two key sources that are used to that are cited when considering flight speed. There's a Pennycook paper based on observations using the ornithodolite that he developed, and there's also the Alistam paper in PLOS, which bases flight speeds on data collected using radar. But as I've just explained, the models are extremely sensitive to flight speed. In fact, the analysis that Liz Marsden's done recently has shown that flight speed is of a similarly sensitive to both the avoidance rate, bird density, and also the proportion of birds at collision risk height. And it's slightly worrying that the data that these estimates are typically based on isn't particularly robust. So, for example, in the Alistam paper I just mentioned, the flight speed for Kittiwake is based on two separate radar tracks, each totaling 660 seconds. So it's not a particularly strong evidence base to be drawing conclusions for such a key parameter from. So there's a need for a much better understanding of how representative any flight speed data is. So people have identified a number of problems with the BAN model as it is, or as it's used, and there's sort of having done a sort of survey of people who use it from industry as well as government regulators and advisors, we sort of highlighted three key criticisms of the model as it's currently used. First of all, people keep presenting single outputs from these models as quite black and white. This is what the number of collisions would be. They don't acknowledge the uncertainty around these values, and that's really important to provide context for the risk. The modelling process at present isn't particularly reproducible. People typically use one of the spreadsheets I showed in one of my first slides and enter the data one by one on a case-by-case basis. This can be extremely time-consuming and very difficult to go back and compare against raw data and to follow the process through from start to end. And I think, given how important collision risk is seen as for the consenting process, I think this is quite a big problem. And as I've mentioned several times already, it also doesn't factor any uncertainty into the estimates of collision. So, as part of a knowledge exchange project, which I've been helping with, Liz Marsden has produced an update of the BAN model, which runs in R and uses Monte Carlo simulations to sample from distributional data for each of the parameters we've highlighted previously, and this sort of allows us to incorporate uncertainty around the input parameters and then follow this through to produce uncertainty around the final collision estimates. The updated model also incorporates wind speed data so that we can now explicitly model the relationship between wind speed and rotor speed and pitch. And we know this is this is potentially quite a key relationship. So it's important to start being able to build in the fact that many of these parameters will be dependent on each other. The model itself is semi-automated, so you can prepare your data and leave it running. It then produces an output of showing the input parameters and also the collision estimates. It produces a couple of useful plots. The first one shows the monthly variation in the collision estimates, and the second one is a sort of probability distribution showing how what the uncertainty around the collision estimates are likely to be. And these inputs can be used within a sort of population modelling context, which, like the one which I'm just about to pass over to Mark to explain in a bit more detail.
Thank you, Angus. So once we've carried out the collision rate modelling, then we will get an output which will be the number of collisions, and that's effectively, we can read that as the number of dead birds, so the level of mortality caused by that development. And we need to compare this and put this into context, and really we do this by looking at in several ways, and as Angus has already hinted about, the results aren't sort of one figure that we can just compare against a benchmark. We need to compare that sort of the scale of mortality and the estimates that we're getting out. And it's always good to compare those to the population and in more than one way. And then we can also compare those methods as well. So really we'll be looking at the level of mortality needed to bring about a change in the population. And then perhaps we could, if we're getting that level of mortality, then we need to look in more detail. And there's several ways of looking at this. One is the 1% of natural mortality. Another one is to apply the level of mortality to population models. And the last that I'm going to talk about is an approach called potential biological removal. So the first method is probably the simplest. It was defined originally for assessing levels of acceptable levels of hunting, and in some countries this has been applied quite widely for assessing human effects on populations. And really we can compare our output to the 1% of natural mortality. And if we get more than that 1%, then we need to look further. So I've got an example here for a population, a breeding colony of lesser blackback gulls in the Dutch Waddenzee. We've got 38,000 birds. We know from various studies that adult survival of this species is just over 91%. So that means that 8.6% of adults would die each year just through natural causes. So that works out for this one colony that over 3,200 birds would die of natural causes each year. So 1% of that is 32.68. Now, as has been hinted, that we shouldn't really go after the decimal place for this. So really, if we're getting figures out of the collision rate model of around 30, then we need to to look at in more detail, we don't have to wait till it goes 32.7. Now, a second way of looking at whether there be any effects on the population is actually create a population model and then apply that mortality. And we've done this several times at Bureau of Edinburgh in relation to wind farm developments. The report shown on the right-hand side at the top, luckily that is in English, and that's available from our website. So that would be the one to look at if you wanted more information. So the first stage, looking at the graphic at the bottom, the first stage, we develop our population model, and we compare this against known populations. Then we carry out our collision rate modeling, and we get out a number of, or a level of mortality. And then in the third graphic, we apply this level of mortality to our population and have a look at the effect. And then the very last stage is we apply as much mortality needed to bring about what we call a zero growth effect, and that's actually where the population is limited through that mortality, so it can't recover. And then we can also compare those figures. So just to show briefly how we would do this, for population models you need quite a lot of detailed information. You have the numbers of the population over time. You need several life history parameters such as survival for different ages, breeding success, age of first breeding, for example. But one advantage, you can look quite specifically at certain colonies or populations, or you could look at larger metapopulations. And something that we've applied to seabirds, long-lived birds, is to have a proportion of floaters. And that's effectively adult birds that aren't breeding, but with the removal of breeding birds, they can come very quickly and replace those birds. So when we apply these in a matrix model, we get something that looks like this, which is starting at the top left. If you follow the yellow circles, that's a bird that's in its first year. And then if we follow the arrows to the right, it will have a certain probability of reaching first year, then a certain probability of reaching second year, then third year, and then in its fourth year it will be adult. They start breeding in their fifth year, where they can, if you follow the arrows round left and back to young birds again, then they can have an influence on breeding. Now you'll see for the adult birds, there's some of the boxes are in green, that indicates a breeding adult, and some are in yellow, that indicates a non-breeding adult. And birds can switch between years. Perhaps they breed every year, perhaps they breed every other year, or perhaps they won't breed at all. So this can be built into the model. We can also build in emigration, and for our study we took a cautious approach of applying density dependence of the maximum counted population. So just to show one example here for lesser blackback gull, if we look on the left, we calculated 850 collisions per year based on a theoretical number of wind farms in the North Sea, and we applied this mortality from around 2010 to the population. And in the blue circle at the top on the left-hand graph, you'll see that the dotted line shows the population level after the applied mortality each year, and the light grey line at the top in that blue circle is without. So it drops slightly below the level, but it pretty much remains steady. So with 850 collisions per year, then the population didn't really drop that much, and it remained quite steady. On the right-hand side, we have our zero growth or decline model, and here we applied as much mortality needed to bring about a change in that population. So again, in 2010, we applied that level of mortality, and it actually took 1,800 collisions a year to actually bring about a steady decline in that population, again shown by the dotted line there. So the last approach, which I'll mention now, is the potential biological removal approach. And this actually looks at the level of sustainable mortality in a population. So it really looks at the potential for population to recover after a level of harvest. It was developed specifically for small populations, although not birds. It has been applied more recently on bird populations. One advantage is it needs less detailed population data than for a detailed population model. So again, in our example for the North Sea, here for herring gull, and I'm showing herring gull here because it's got at the moment in the North Sea a declining population. And our results from the collision rate modeling for 11 theoretical wind farms in the North Sea was 585 collisions. Now, if we applied these to our population model, we already had a decline in population, so it just made the decline faster. So applying a PBR approach, we found out that the population could actually sustain 1,200 collisions a year, and that was even with a cautious approach of treating the species as near threatened. So that's with a very low ability to recover and a very small population. Most importantly, with all these methods, as I've indicated at the start of this section, is there's not one approach that's better than the other. The best approach is to compare them all and evaluate them all. So this hopefully gives you some indication of what we can do with the results from the collision rate modeling. And I'm going to hand over to Angus just to finish off and show how this fits into the legal context.
So from a regulator or advisor's point of view, the sort of key question is usually, so what does this mean for my birds? Once presented with a sort of collision estimate and this population model, the sort of process is to say, okay, well, what does this mean for the population of birds at my protected sites? And they've got a sort of process which they work through, but really the key question is this wind farm going to adversely affect the integrity of my site? So I think the key phrase there is adversely affect, and it's sort of perhaps not immediately clear what that means, but it sort of links back to the conservation objectives of any given site, which sort of say that the population of the birds present must be either maintained or restored, and it must ensure that any of the impacts arising as a result of the offshore wind farm do not cause the population to decline. So these sort of impacts, as Mark sort of highlighted, can be assessed in a variety of ways, using a range of metrics you could derive from a population viability analysis, like the proportion of whether or not the impact causes the population to decline, the sort of a comparison of the impacted to unimpacted population, a comparison of the growth rates of impacted and unimpacted population. There's a variety of metrics that you can then derive from a population viability analysis to determine what sort of impact the wind farm is likely to have. You can assess it against, you can assess your sort of population level impact against the potential biological removal, as Mark's just highlighted, or you can use approaches such as acceptable biological change, where you sort of look at your impacted population and see if it overlaps with the sort of 66.7% confidence interval surrounding the an impacted population. However, I think at this point it's key to highlight that the suitability of a lot of these metrics is subject to debate, and I think, as Mark highlighted, there are issues with all of them, and I think some of these key issues relate to things like uncertainty in the demographic parameters that are used to estimate the metrics. There's uncertainty in the level of the predicted impact, and this uncertainty is something that we're starting to get a handle on through more advanced modelling, such as changes to the sort of collision risk models that are being made. And there's also a question mark over how relevant some of these are to the conservation objectives against which they're being assessed. So I think these methods all have sort of advantages and disadvantages, but it's important to be aware of some of the issues surrounding them. So to sort of wrap up and summarise the sort of talk, I think collisions are generally considered to be one of the main impacts of wind energy on birds, and you can sort of pre-construction you can use things like collision risk modelling to assess what the effects are, and this is particularly useful in an offshore environment where things like searches for collision victims just isn't feasible. But these models need to be informed by field data, so data collected on things like the number of birds present, the height birds are flying at, the avoidance rate of the birds, and actually another key thing that they need is much better data on the flight speed of the birds present. Having done your collision risk modelling, you can then sort of assess the number of collisions in relation to a whole range of impacts. For example, the 1% criterion, or using population models, or potential biological removal. But it's important to compare this consider this in the context of the population and also any other pressures that might be acting on the population concerned. So I thank you for listening to our talk. If you'd like any more information, our contact details are on this slide here, and we'd be happy to answer any questions that you might have. Just pass back over to Elise.
Thank you all. Thank you very much for great presentations. At this point, we would like to open it up to questions and answers. A couple people have sent in some questions. I can read one off, and then we can quickly turn it over to allowing people to ask the speakers questions directly. This question is, if you were able to produce measures of uncertainty in your estimates, how would you suggest they be used? For example, your graph of PVA showed a lower limit crossing 1 when collisions were quite low, but the upper limit crossing when collisions were quite high. Which would be the relevant level for management and conservation purposes?
I think when assessing the sort of impacts to population level, we generally take a precautionary approach. So what's the realistic worst case scenario? And so in that instance, I'm not sure if Mark's got a different opinion on this from me, but in that instance I would assume that you would be saying that the line crossing 1 would be the realistic worst case scenario. I'm not sure if Mark agrees with that or not. But
yes, I agree with the approach. If we're uncertain about things, then we have to take a cautious approach, but realistic approach.
Thank you. Colin, will you walk the group through how to ask questions?
Certainly. Ladies and gentlemen, if you would like to ask a question today, you can do so by, first of all, you can write in your question if you'd like by using the Send Note button in the top toolbar, or the Notes tab on the right-hand side of your screen, and you could address those to presenters. Or if you'd like to ask a question over the phone lines, you can do so by pressing *1 on your telephone handset, and you'll be notified once your line is unmuted. And if you press *1 a second time, that will remove you from the question queue. So again, that's *1 if you'd like to ask over the phone, or you can use the Send Note button in the top toolbar if you'd like to type in your question.
So I have a question from Benjamin Callard, and that asks if the R application of the BAM model is available and where can it be found? I think probably Angus can answer that.
I think it's not available yet. I think it should be available very shortly in the next month or so. I think Liz is just finalising the documentation for that just now, and we'll be making it more widely available soon.
I've received another question from Luke Feinberg, and that asks, were the impacts of climate change included in the population model estimates? And I think that refers to the last study that I talked about and showed those population models. And the answer is no. We just included wind farm effects. So we didn't make any additional mortality for future estimates, for example, of climate change or any other human pressures. We only looked at pressures of future wind farms. So hopefully that answers that question for you.
Okay, I see a question on here that I could read off. It's from Sherry Metzner. It says, how are digital aerial surveys used to determine flight height?
That's a very good question. Unfortunately, I'm unable to answer it. There's a couple of companies concerned who have been able to estimate flight heights from digital aerial surveys, and whilst they've been able to share their methodologies with us, because of the concerns over commercial confidentiality about that, I'm not able to discuss them more widely at this stage, I'm afraid.
We can move over to just a quick discussion. If we could display the slide of future potential webinar topics while we still have folks on the phone, that would be great. Thank you. On your screen right now are some potential future webinar topics that have been brainstormed within the WREN member community. These topics are on your screen, with the first out of for the next quarter being on sensitivity maps. For the fall, looking into moving into offshore mitigation techniques, and then to wrap up the calendar year to focus on sensors and things like recognition software. We would be very interested right now if there's folks willing to offer opinions, suggestions on potential future topics of interest, and that would warrant a deeper discussion with this large community of stakeholders. That would be helpful. We want to make this webinar series as useful as possible to help advance the industry and reduce barriers to wind energy development. I am getting some more questions I can read off, but interspersed in there, if you would like to verbally offer some advice or opinions on our future topics, that would be great, or you can send it to us in writing at any time. But in the meantime, here's a question for our speakers. Well, where can we download the presentation? We will have that on the WREN Hub, and where you went to get the call-in information. All the presentation that Mark and Angus gave today will be located there, as will all previous webinars and hopefully future webinars as well. Comment or question from Ross McGregor: is the sensitivity of the CRM output not a function of avoidance rate? As the AR tends to 100%, the collision estimate tends to 0. So the higher the AR, the less important the other parameters to the final value.
I don't think so. I mean, so when Liz did the sensitivity analysis, she held the avoidance rate constant and looked at what impacts varying each of the parameters over a given range had on the collision outputs, and she found that there was similar variation in things like flight speed as there were with things like the avoidance rate. Hope that answers your question, Ross. If not, please send me an email and I'll try and explain it to you in a bit more detail.
Thank you. Here's another Diana Dishman. Can you please let us know what the name of the BAND-R model package, when it is released?
Yes, I can do. If people want to send me an email or something, I can either put them in touch with Liz, or I can send them a link to where it can be downloaded.
And another, again, the PowerPoint presentation will be available on the TESIS website. I'm getting some feedback on some of our topics, support of some of the topics that we've already put out there, so that's terrific. Particularly the offshore mitigation techniques and sensor and sensitivity maps. So we'll definitely stay on that course. Manolo Huso says, have you or would you be interested in conducting a multi-site study in which collision risk model predictions are paired with fatality estimates from well-executed fatality monitoring studies? Of course, this would only be possible onshore at this point, but do you feel it could provide valuable feedback for confirming CRM predictions? As an aside, I much respectfully disagree with your comment that counting collisions is quite straightforward. And there's
I think the answer to that is yes. I think one of the key issues with collision risk models is that I'm not aware of any studies that have attempted to validate them, and I think that's a major shortcoming. And I think we need to look at how we might be able to validate them, and the sort of study that Manuela suggests would certainly help with that sort of thing. And I think the counting collisions is quite straightforward. I think that was a sort of a relative statement, so it's quite straightforward onshore relative to counting collisions offshore.
Yes, it's Mark here, and I agree with that statement and Angus's answer. That the comment that counting collisions is quite straightforward was with regards to potentially other situations where it's completely not possible. And you're absolutely right that there's a lot of other factors to consider. It's not as simple as just going out and seeing what we find. There's certainly another factor, numerous factors to take into account. I would just follow up on Angus's answer. It's very useful, and we've actually in the Netherlands carried out such studies where we've looked at the potential estimates of what we would expect and compared that to actually what we found. And based on those data, there's actually a redevelopment of an empirical model that's in preparation for publication at the moment. And the advantage of that is we're actually, if you like, taking out some of the estimates for avoidance, because that's built in to where we're actually counting the fluxes or observing the numbers of birds flying through an area with the numbers we're finding. So there's obviously limitations to that approach as well, but it is extremely useful, and again for cross-referencing theoretical models.
Thank you. Here's another question from Miguel Repas. Most of the examples we have been seeing on the application of CRM are related to seabirds with linear flight movement patterns. They will just fly in straight lines. Where do you see the limitations for CRM models for species with nonlinear flight patterns, such as soaring raptors on updrafts and feeding bats? How will these flight patterns affect collision risk estimates?
I think the answer to that is that they will affect collision risk estimates. I'm not sure we're at a stage where we can say how they'll affect them. I think this is actually quite an important point. It's something that I'm very interested to. I think Miguel says that talks about seabirds having linear flight movement patterns. I think that a lot of the stuff from that's coming out from the tracking studies at the minute shows that certainly in some areas they don't have linear flight movement patterns, and I think it would be really interesting to understand how that might impact collision risk. And I think you could I certainly have in my head an interesting study you could do to sort of look at how comparing how a sort of straight linear flight would affect collision risk as opposed to a sort of more variable flight path intersecting with turbine rotor areas in different ways. And I think that would be something that would be well worth doing.
If I could just add something in reference to bats, which are mentioned also in that question. I know for bats there are very different models, that the high risk time for bats are actually when wind speeds are quite low, and quite often when wind turbines are just idling and not actually generating any energy. So it's a very effective approach has been to effectively put them on the brake so that they're not idling at low wind speeds, and that is my understanding from it's a very simplified answer, but it's a very different approach for bats than it is for birds. And I've got one other question directed to me in relation to wind speeds and bird behavior and flight speeds. So the question says, most of the sea surveys are made in calm and windless conditions. How do you institute the change of behavior in stormy or heavy rain or other difficult conditions in the collision model? For example, shear waters especially can have very different behavior. That's absolutely true. The other part of that question referred to flight speed. So flight speeds most flight speeds are recorded relative to airspeed. So with strong winds, the ground speed will be very different as well. And that's absolutely true. Bird behavior itself will be expected to be very different in strong wind conditions, perhaps stormy conditions, than in calm conditions. And based on radar data that we have, which are recorded not in extremely stormy or rainy conditions due to mechanical limitations, but we're also recording at night, which sea surveys aren't done, then it is possible to sort of have a feeling about the difference in bird behavior, and we're certainly seeing that birds are avoiding the area completely in stormy, windy conditions, or that would be a feeling. So perhaps birds in calm conditions are more confident of their ability and would fly into a wind farm and then avoid at a closer scale, a macroscale. But in stronger conditions, they would just stay completely outside it. So that could be one response, but data are lacking to back that statement up. That's more of a feeling from what we're seeing, but no hard data.
Yeah, I mean, I think this is something that we can start to get a bit more of a handle on it with some of the tagging studies that are going on at the minute. We mentioned the lesser blackback tracking work that both Bureau of Edinburgh and BPO are doing just now, and that certainly has tracks of birds in and around wind farms, so we can start, hopefully we'll be be able to use this sort of tagging data to start to draw more inferences about how birds are likely to respond to wind farms in different conditions.
I have another comment here. Abbas Jafari says he lives in, I'm sorry if I mangled the name here, Babelsar city in Iran near Ferry Dunkinar International Wetland, can participate in studies about migration birds in that area. I don't see any other questions here. Do any of the other presenters see questions on their end?
No.
Okay, thank you. Oh, we'll end the call at this time. If you can look, can you move one more slide up, please, for the contact information? Thank you. Karen Sinclair is our operating agent for IA Task 34, or WREN. The operating agent is a partnership with DOE, NREL, and PNNL, so any of us could be contacted at any time, or any of the members within IEA Task 34 at any time if you have questions or comments or suggestions for future topics on our webinar series. Also, as you can see on this last slide, is the link to the WREN Hub, as well as IEAWIN.org, where you can navigate to Task 34 for more information about WREN. We're very excited about this webinar series, and particularly this call has brought a lot of interest. We had over almost 120 open lines for this call, and so that is indicative of a topic of much interest, and perhaps we can get into this topic again more deeply on a future webinar. So please send us some ideas when you can, but we want to make this series as useful as possible for the industry. Thank you.